Hi guys, welcome to week 8 lecture series, lecture in our module entitled Load Calculation. So load calculation, just like psychometry chart, is divided into two sections. So part 1 and part 2. So week 8 is part 1. Okay, part 1. Alright, so let's go to Times page and let's see where you can find this lecture notes, and of course where is the location for the tutorial for week 8. Okay, let's go. Hi guys, welcome to our lecture. I put the week 8, right? Week 8, so load calculation part 1, but here I have the notes says lecture 6. So I didn't bother to change because throughout the text it will be 6.1, 6.2, but here the content is still the same. It's taught in a different week. So you are week 8, load calculation part 1. Okay, so let's go to the chapter details. So we have 7 chapter details. The first one is the basic concept of load calculation, the outdoor design conditions, indoor design criteria, what are the cooling loads principle and components, the heating load, finally examples of non-residential load calculation. Okay, alright, so we'll go to the first one, the basic concept. So the basic concept is to cool down. To cool down who? To cool down the occupants and to cool down the computer. So technically heat is going to move from a hot place to a cold place. That is thermodynamics rule number 1, right? Because heat mainly comes from the solar radiation, this heat will seep into the walls of the building, right? As well as other components inside the room which also emits radiation, and also finally the body of the occupants themselves also emit radiation. Okay, other than that, there are conductive heat gains, heat that comes from anywhere, any source outside the house or outside the space, and also infiltration, which is creaks or cracks that happens on the building's facade, which allows unnecessary hot air or sometimes cold air into the room. Okay, so the thermal load, which is the basic concept, is how much heat is going to be removed or added from the space. So the objective is just to maintain the proper temperature in the space. So here you have on this picture and diagram, the optimum picture in Fahrenheit is somewhere between winter and summer, which is around 75 degrees Fahrenheit. Okay, so 75 degrees Fahrenheit is from down here up till up there. Okay, the difference is it has the same dry bulb temperature, but the humidity is different from this point right to the top. Okay, which is also brings latent heat and sensible heat cooling load issue. Right, when thermal loads push condition outside the comfort range, HVAC systems are used to bring the thermal conditions back to the comfort condition. So if it's in the winter, the outdoor air is cold, the aircon system not to cool down but to maintain a space of 24 degrees Celsius. So basically the aircon will act like heat pump. Okay, either to cool or to make place become hotter. Okay, to maintain the space within the limit of required by the occupants. So the purpose of HVAC load estimation is we need to calculate the peak design loads. What is the maximum of this aircon system can have, other than to have it as strong as reliable as possible, but also we want to know what is the estimate likely equipment's capacity or size needed to cool down a space on that thermal comfort zones, and also to provide info of the HVAC design, for example the load profiles, which is also important for other people to read the report and manual. Right, lastly, to form the basis of building energy analysis. So from here you will have the cooling load calculation. Right, so the main target: important warm climates and summer design. also affect building performance, and its first, cost. Okay, so heat transfer mechanism, we have done this in thermodynamics class. Of course, it is conduction, convection, and radiation. So the thermal properties of the building, overall thermal transmittance, which is the U value, which is also, you have learned this in thermodynamics class, thermal conductivity, and finally thermal capacity, which is the specific heat inside the space. Alright, however, before we go further, let's review thermodynamics for a while. Okay, so we have 1, 2, 3, 4, 5 plus items of thermodynamics that I would like to touch a little bit before we go further in the cooling load situations. The first one is the Fourier's law. Next is thermal conductivity. Next is one-dimensional calculation, convection and radiation, and other than those, Stefan Boltzmann law, Blackbody radiation, emissivity, and lastly, absorptivity. So what you're looking at right now is the Fourier's law. So Fourier's law is actually the basis of the thermodynamics law that talks about the conduction of heat through a material, right? So here you can see there's a wall. You can read this whole section here, but I'm going to talk about this wall. So this will have an X there, delta X. That means it will go across this cross section of the wall. T2 from the outside or from wherever this T2 comes from is higher than T2. So therefore, heat will transfer from T1 and go to T2 with the coefficient of the Q that is transferred through the medium, right? Because of the difference of T1 higher than T2, and therefore Q will cross from T1 to T2. Okay, so this is the very basis of equation that talks about, okay, let me write it down, Q dot M dot Cp T1 minus T2, right? So this is the basis of that equation, Fourier's law. Okay, so it says here, if delta T and delta I is constant and varying A, that means A is varied, A is a surface area, then Qx is directly proportional to A. That means the bigger the surface, the bigger the Q. The smaller the surface, the smaller the Q. If delta T and A is constant and X is varied, that means the depth or the thickness of this wall is varied, then Qx will be inversely with delta X. That means Q will be exponentially lower when it crosses this thick wall. If delta X and A is constant and varying delta T, then Qx will be directly proportional to delta T. Okay, if temperature is varied, that means increase or decrease by itself, then it will be Qx directly proportional to delta T. So that is Fourier's law. Okay, so basically it will talk about Qx is directly inversely proportional of A with the function of delta T and dx, right? So the bigger the dx, the smaller the Qx. The bigger the dt, the smaller the dt. Also Q as well. The bigger the surface area, so the bigger the Q as well. Okay, so if we change the material, we also find it is abovely proportional remains valid. If this wall becomes concrete or metal or any kind of materials, this equation stays the same, right? And also, if we change this inversely to be proportionally, this delta minus K or K should be added, or K is called the thermal conductivity, which says that Q will decrease as it goes through the wall, right? The magnitude or the quality of Q will decrease as it crosses to the wall. Thermal conductivity for all materials are given in this table. You can have it more inside all the ASHRAE handbook and maybe online if you like, right? So these materials have its own K. So if these are asked in the exam question, then the K will be given as well. Right, these are other example for K as you can see here, so you can read it yourself. Now, we always talk about one-dimensional conduction that goes through one X, right? One X, and sometimes we do talk about two-dimensional conduction. As you can see here, this T1, T2, T3, and T4 heads, it has its own K, and you can predict that for K2, for material number 2, even though the thickness is small, but there's a huge decrement in the quality of Q. That means its K is quite high, quite high. So this is what we call in conduction as conduction through material in series. Now, you can use the analogy of electrical resistance. Current is I, voltage divided by resistance. Okay, so I can be decreased if the resistance is increased. Is similarly, if you use a thermal resistance for heat transfer, if thermal resistance increase, Q will be decreased as well. So this is the basis of one of series connection of conductivity in terms of heat or thermal energy. So using the same concept, you can put the series in terms of this way. So if there's any question asked about what is T1 and T2, given the resistance, you can answer this question using this relationship. Okay, and also you can line it up with this method because you have just now like this, right? So you can combine them in this series, right? And also you can change R into X divided by KA. So basically this is just changing the algebra of the equation. Right, this is also an example. You can read yourself, but the answer I will not give. So you try yourself, and surprise, surprise, this will be the submission for attendance of week 8. Right? That is for series, and this is the analysis that can help you with that question. Next is the parallel connection. Just now the materials are lined in series, now they are lined stacked on top of one another, and we call it as parallel. Okay, parallel. So this method is 1/, right? This 1/, is a method of parallel, which is also popular if you use ohmic resistance. If you have a combination of series and parallel like this, so the equation will become something like this, the one that I show here in the laser pointer. Now there's also another example which does not have any answer, and therefore this will be also used for your submission for attendance. Alright, so these are some of the data that will be given to you of insulation of building. Right, so if you have insulation of building, this is what we call as double glazed glass, right? This is one method to conceal or to prohibit heat from moving from 20 degrees Celsius space indoor towards outdoor. You can still allow light to go through this glass, but the glass will be an insulation from the heat to move from one point to this point, right? From indoor to outdoor. Okay, so next part is the convection. So convection, if I can read from the slide, heat transfer that will occur between the surface and the moving fluid when they are at different temperatures. So I believe you are familiar with what convection is, and usually convection happens in fluid or bodily water or bodily liquid. There are two parts of convection. One is natural convection, one is forced convection. The natural convection usually happens naturally, but forced convection usually happens with the help of mechanical devices or human interaction. Okay, so you can see here that this pot will have a natural convection, and also another example that a house has a warming of a room using a hot water radiator, which is also a form of convection. A forced convection is like you blow a hot noodle that you can eat afterwards. And of course, another one is any fan inside any computer case to cool down the components inside the computer. Okay, now convection of a double glass window also can be used other than the usage of conduction, right? So in the exam, if the word is conduction heat or conduction with the method of heat, or if heat with the method of conduction, you will use conduction method. But if the convection, you will use this equation. Okay, K is similar to the one that you know. X is the thickness of this glass, right? Okay, so you will know that. Okay, so if the question use convection, then this is the equation to use. Okay, Newton laws of cooling. For heat convection, the rate of equation is determined by Newton's law of cooling. So Isaac Newton devised this Q convection, right? So you know that Q conduction already, Q mCp delta T. Sometimes Q is equal to m delta H. But if this is convection, that is H times A, or the surface area, times the difference between the surface minus the environment. Okay, my environment. Or here it says the fluid temperature away from the surface. So this is the equation for convection, which is Newton's law of cooling. Then the last part is radiation, which is energy radiated by matter in the form of electromagnetic wave as a result of the changes in the electronic configuration of the atoms and molecules. Anything that heated up will emit radiation. Okay, for example, radiator inside your room, the computer, your body, the light, solar radiation. Okay, energy transfer by radiation is the fastest and most efficient in terms of heat transfer. Okay, so we are interested in any form of radiation related to thermal value, right? Solar radiation, computer, so on and so forth. Other thermal radiation, radiation such as X-ray, gamma rays, microwave, radio wave, and television wave are not included in this module because they doesn't introduce heat into the space. Okay, another thing, another part of a Q, which is a Stefan-Boltzmann law. Heat is transferred using the Stefan-Boltzmann's law. Then this is the equation. So what is it about? It is a volumetric phenomenon of all solids, liquid and gas that emit, absorb or transmit radiation in varying degrees. I really ask this because our Q is based on thickness of material as it crosses the panes or the glass or the walls. This is the radiation that emits in the environment. Okay. If we talk about Stefan-Boltzmann, we're also going to talk about Blackbody radiation, where a body will emit radiation as if it is a black body, because a black body absorbs and emits radiation at the most effectiveness. If a black body emits radiation, equation is E, where E is the emissivity. So if you have emissivity, it's between 0% to 100%. So it is based on material or what kind of black body that emits radiation, E will change. Alright, E will change. But for a black body, E will be 1. E will be 1. Okay, these are some of the example of emissivity of a body. So absorptivity is the opposite of emittivity. So if a body can absorb radiation, so the body can also emit radiation. So alpha equals to 1 will be the body is absorbing the radiation very effectively. However, because light tends to bounce on the surface, and therefore the radiation or the electromagnetic will bounce as well. A part of it will go inside and a part of it will be expelled from the surface. So Q incident will go and touch a surface, and then Q reference will be reflected, and whatever is going to be absorbed is ABS into the surface. So if this body is totally black or fully black, then everything will be absorbed already. right? Everything will be absorbed. There will be no alpha here. Okay, so this is the equation for Q emit or emittivity. If we have absolute temperature. So if we talk about absolute temperature, this is the equation, and this equation will be given in the exam. So don't worry. Another part or another term in this section, thermodynamics, is heat gain, where energy is transferred to or generated within a space, and then the heat is gained through latent or sensible heat, which we have discussed in the psychometric chart lecture. These are some of the example of how heat is gained inside a space that you can read yourself, yeah? Then, this is a term called infiltration, where cold air or hot air move from one space to another by the cracks of the material. It is not opening, it is not window, but a cracks of material. Okay, so the difference of pressure between one place to another brings the heat through this infiltration. Maybe this place is cold, what I point with my laser pointer, and this place is warm. So the cold space will use a higher cooling load because there's infiltration. So you can see here in the picture, this room look nice, nothing wrong with it. But if you use with a thermal imaging, you will see that there's a heat leaked through these infiltration sites. Yeah. So the fenestration happens when you have glasses, a huge glass door, huge glass wall. You have high level of fenestration. So you can read here what is the example of fenestration. Right. Basic concept. A building survey will help us achieve realistic estimate of the thermal loads. The orientation of the buildings, where does the facade of the building is facing, how many space do you have, how many physical dimension of space do you have, what is the height of the ceiling, what about the column and beams, how many do you have, construction material, what are the material of the building that you are staying in, surrounding conditions, right? Maybe where does your space is situated, right? And also where is the location of windows, doors, stairways, and other components of housing. Okay. Building surveys can also be done on how many people, what kind of lighting or electrical equipment, like appliances, and also ventilation, any thermal storage or continuous or intermittent operation. For example, maybe the room is placed for heavy activity for a small period of time, and suddenly the activity is stopped. Maybe it's a place of like a market, or maybe it's a place of temporary offices, okay, something like that. So you must know the dimension of the house, what kind of furniture you have inside it, and what is facing where. So for example, like this lengthy of building is facing towards the north. So if this is north, this one will face east, and this one will face west. Okay, it will face west. Alright, for outdoor design conditions, it is used to calculate the design of space loads. Usually it's a climatic design information, where does this space is situated, right? Latitude, longitude, latitude, atmospheric pressure, so on and so forth. The outdoor design conditions, to derive statistical analysis of weather data. Typical data can be found, you can find it in books like ASHRAE handbooks. Also, sometimes you can use the online reference, okay, to find the outdoor design conditions. So places on Earth will have different latitude and longitude, and will also have cooling, evaporation, and dehumidification, and also extreme annuals inside a year. So you can use this data to design and condition a space, right, based on the location. Alright, you can find this data from ASHRAE. Cooling and dehumidification design conditions, cooling dry bulb, mean wet bulb, dry bulb temperature, mean condition wet bulb temperature, evaporation, heat dehumidification, and mean daily range of dry bulb temperature. You can find this data in terms of outdoor design condition. Alright, the basic design parameters for thermal comfort is the air temperature and air movement outside the house, outside the space. What is the outside space relative humidity, and also the comfort zone in each of these locations, which are different, because when we talk about spaces and location, a building which is situated high above the sea level, maybe on the mountain or on high hills, right, you will have lower humidity or maybe cooler spaces. So there are differences in design of outdoor air condition. Indoor design criteria will be also climatic, annually, monthly, and hourly data, the degrees of days, and also the typical data set. So you can also use this X-ray climatic information to design indoor conditions, which will in turn promotes the thermal comfort inside the building, right? Maybe in summer and also in winter. And also the one immediate here will be the thermal comfort. So this is the indoor design condition. So the indoor design condition must meet the thermal comfort, right? Also, other than that, we'll talk about indoor air quality, about air contaminants, outdoor ventilation rate provided, and air cleanliness as well. Okay. Sometimes noise also is included inside the conditions of designing a space, but although it is not going to be included in our case because it is not thermal based, right? Thermal based. Alright, so that's all for part 1, where we stop at indoor design criteria. Will be next week or next video. We will talk about cooling load principles and components and heating load as well, and some of the example. Okay. So thank you for joining my week 8 load calculation lecture, and I hope you can get some information, and I have shown you some criteria when designing space, right, other than indoors and outdoors, and also the components that you have inside it. What are the criteria that is important when you want to design a space, air conditioned space? Okay, I will see you on week 9 video on the part 2 cooling load or load calculations. See ya.